Hi guys, welcome to this second session of this week. We are actually in the week before Thanksgiving. I know we introduced this topic last time, and actually today is one of the important topics that needs to be discussed. I know some of you are sitting in the lab version of this class, namely Astronomy 125. And in there, we had an interesting topic yesterday, namely the classification of stars based on their spectral properties. And this is actually based on this discussion that we're going to have today in lecture. So in a sense that the lab was actually leading the lecture in a sense for some of you guys. I know others are actually sitting in the other section of astronomy, at least in my class, and we already covered this topic before the lab. So the late start class had a little bit of a delay in terms of the topics, but that's fine. We covered it yesterday in lab. And we talked about basically the different classifications of the star, namely the O, the B, the A, and F, G, and K, and M, at least those the main ones. And those part of something called the HR diagram, which we'll be covering today. So the first two topics are actually not that big in terms of content. And the last one, actually, we're going to have several units down the road to discuss them. So hopefully you guys are going to be, we're going to get them into a little bit more in depth down the road. Granted that we have a week break, which is this coming week, which is Thanksgiving break. Then when we come back again, we have quite a bit of materials to cover. So hopefully we'll catch on with it and we'll deliver them in time before the final, which is going to be the week of the finals, which is the second week in December. So we have also other assignments, so please make sure you follow on those, namely the discussion sessions, the quizzes, and all of those things. I know Thanksgiving is a holiday and you really need to take care of your family needs and so on and so forth, but it's important also that you keep up the work in here so that we don't forget that we have quite a bit of material to finish before this class is over. So let me share with you the screen and go to unit 57. We have 3 units to cover today, 57, 58, and 59. And 58 actually deals with the binary stars because they're an interesting topic on their own. And also they help us understand the stars, okay, better. Because once you have a tool, you would want to take that tool and make models out of it. And then now you see something else. You see a brand new star and you would want to identify it. So it's a good idea to compare to what you know. This is actually the technique used. And the binary stars have an interesting advantage over the others in the sense that you have 2 stars that are orbiting one another. And in doing so, if you determine their rotational speed, namely their velocity with which they spin, namely the angular velocity in this case, the period, the time it takes for them to go once around one another. That is a part of a formula that we know how to handle if we know the distance between them. And if we know the distance between them, that is A. So we know that P squared, or if it's expressed in years, is equal to A cubed. That's the third law of Kepler. But in this scenario, it's part of a binary. So we have to really be very careful in here and modify it. Once we have it modified, then we're going to get the sum of the 2 masses. So now we have a piece of information of these stars. If I find how far is this from their center of mass and how far is the other one is from their center of mass, now actually I can find the 2 masses, mass star 1, mass star 2. If I can tell how far they are, then I have a lot of information. I'll have the temperature based on the surface, basically the maximum wavelength. I can know the mass, I know the distance, I know the size. So I have information now about the stars. And mind you that binary stars represent about 50% of the stars out there. So it's half the stars out there are of this type, okay? And that's plenty of sample, because if you have billions of hundreds of billions of stars, that's a lot of materials to study anyway. So it's an interesting topic. Again, the binaries, they come in different flavors. Some of them are basically, you can visually see them, okay, with pictures. Nowadays, for example, part of a binary that we can study is actually Proxima A, not Proxima, Alpha Centauri A and Alpha Centauri B. Those are binaries that are actually nearby, the closest stars, binaries to us. Proxima is actually part of the system too, but still a little bit far away from them. That is two stars next to one another. There are actually another example, which is series A and B. Those are all actually two binaries. Granted, one of them is a main sequence star and the other one is a white dwarf, but it's a binary. And now with the James Webb, you can actually see the two stars, a big star, which is A, and a dot next to it. That is actually what B is. Okay. So that is basically, it's an advantage. So those type of stars that you can see are visual binaries. And there is another one where if the two pictures are blurred to one another, and you can dissolve them with the spectroscopy, those called the spectroscopic binaries. And then there is one, if they are actually happen to be on the edge on, so you cannot see their distinct spectra, but you can see they're an edge on. Then in this case, one of them can go in front or behind the other one on a regular basis, and those are eclipsing binaries. So those are the main types that we can study from Earth in here. So in the case where, I mean, look, if a star is moving towards us, and if it's part of a binary, its spectrum is going to shift toward the blue. Remember, if I take, for example, hydrogen, which is the main element in the atmosphere of a star, and if I can look at its absorption spectrum, namely light is leaving the star, it's absorbed by the hydrogen atoms in the atmosphere of the star, and as it's absorbed, it's going to leave those frequencies out of the spectrum. Okay. Now, this is an absorption spectrum, so it's going to appear as dark lines from the spectrum. Now, if the star is moving towards us, this spectrum is going to be shifted toward the blue. So it's a blue shifted. It doesn't mean that the colors are blue. So the red stays red, but it's slightly less red than it was before, what it should be. And if the star is receding away from us, it's moving away from us, then again, the spectrum will be shifted toward the red. It doesn't mean that the blue color is red anymore. It means it has shifted. It's less blue than it was before. So that's basically how the Doppler shift effect. So armed with this technique, we can use it for a binary. For example, if we take the Alpha Centauri system, which is made up of two stars, A and B, that's called Alpha Centauri A and Alpha Centauri B, and modify Kepler's laws. So remember A cubed, that in astronomical units, and P in years. When you take the cube of the distance between them and you divide it by the square of the time it takes for them to go once around their common center of mass, because they're not revolving around each other anymore, because they're relatively the same size. One of them is slightly bigger than the sun, and the other one is slightly less than the sun. So they're relatively big size, I mean, similar size. Alpha Centauri system is not part of the mainly the northern skies. It's really part of the southern skies. That's where you can see them. But the point being in here, you can find the sum of the masses using this technique. So this technique will give you the sum of the masses in terms of the sun, the mass of the sun. So the combined sum of these two is just slightly under twice the mass of the sun. So how does this will help us in trying to determine their masses? If we can find their very center, if we can find their common center where they're revolving around, okay? So if you see a circle, trying to find the center of the circle, that is the common center for both of them. Now, armed with that technology, or armed with that piece of information, I have two equations. I have an equation that gives me the sum of the two, which is just the cube of the distance divided by p squared. So I have that constant. So this is a number, like 12, okay? I know it's not 12, it's 1.9, the sum of the mass of the sun, okay? So this is like 1.9, the mass of the sun, okay? The sun mass. Okay? It doesn't matter what that number. I know it's 10 to the negative, 10 to the positive 30. So that's roughly how much it is, kilograms. But now we know, if I know the very center, we have another equation, the mass of the star, which I don't know, times how far is it from the common center, must be equal to, this is how you find the center of mass, by the way, between any two objects, okay? Is equal to the mass of the second star times the same distance between the other two. And again, remember the A is just the sum of these two A's. A is how far the star A from the common center. So this is star A, and this is star B. and this is what I mean by AB, and this is what I mean by AA. The sum of these two is the distance that separates the two stars, A. So A is AA plus AB, and that is the sum of these two. So there is a little bit of algebra in here, but it's really not that complicated, honestly, once you determine how long it takes for the star to revolve around the common center of mass and how far is the center of mass from each mass, then that's it. Then now you can find the masses. So now we have a new piece of information that we're going to add to the puzzle. Ultimately, we're going to put them together and study them, and we're going to have that in what is known as an HR diagram. For the main sequence stars, okay, for the stars that are not part of the main sequence, we really have to have a different technique for them. Anyway, the other piece of the puzzle is trying to determine the size of the stars. Really, that's how the whole thing is. Now, if I know the temperature, if I know the size, then I know how much energy is output from that star. So if I know T, that will help me to find how much energy is being emitted per unit area per unit second, per unit time, I'm sorry. So this number is just 5.67 times 10 to the negative. So ignore the sigma, now I put lowercase sigma, just it's a constant, okay, just 5.67 times 10 to the negative 8 times temperature to the power 4. Remember, the temperature is given by Wien's law, which is 2.9 times 10 to the negative 10 to the power 6 divided by the maximum wavelength, which is measured in nanometers. So if I can find the peak frequency or the peak wavelength, I can find the temperature. If I find the temperature, I can tell you how much energy is being emitted per area, per unit area. But if I don't know what the area is, then I can't tell honestly how much I have. So if I find the radius of the star, then I'm in business. Then we know all of the information that needs to be known about the star. So again, it's very hard to measure directly, but use techniques. For example, the interferometry for not too far away stars from us, that can use basically either a large array of telescopes, and based on that, you're going to find some sort of a picture, a more refined picture of a star. Other techniques, like for example, the transition for an eclipsing binary star. Remember, an eclipsing binary star is made up of stars that one of them orbits the other one with the line of sight there, and they happen to be exactly in the line of sight of the Earth. Then in this case, one of them at times will go in front of the other one. And if it does, remember, the earlier light is the combination of the two stars. In this case, I have a small star and a big star. The small star will go in front of the big star. So it's going to, in a sense, is going to shield a little bit of the other star. When it does, during that transition, basically, I have a dimming effect in this case. But it's still a combination of the big star and the small star. But if it goes now, when it goes away from it, then I have back into the normal brightness of the two stars emitting at the same time. Remember, this is an exaggerated picture. They're very close from each other, relatively speaking, because they're far away. Even though they may be very, very, very far away, they may be even several hundred astronomical units away from each other, but they appear to be one dot from far away. But if I can see that the light is dimming regularly, and it's dimming more when the brighter star goes behind the bigger star, because now its light is completely shielded by the big one, which is less temperature. So there's a big dimming in this case. Then I can tell you that I am, first of all, dealing with an eclipsing binary. And not only that, but also that eclipsing binary, it can find how fast it's moving based on these properties. So, and can find also the size of during the transition, the size of one star, relatively speaking, with respect to the other one, and so on and so forth. So a lot of information can be deducted from this phenomenon. And now I have a rough estimate of the sizes. Then using Boltzmann law, again, that I was describing in the beginning, then I have how much light is emitted. So now I have a lot of information. So we can find binaries, we can find their radii, we can find their masses, we can find their temperatures, we can find all kinds of information, now their luminosity. So we have basically a base knowledge now. Remember, we have billions of stars out there. So this is still leaves us with tremendous amount of pieces of information that we're going to be able to put together. enter the HR diagram. So what the HR diagram tries to do is summarize all of this information. You take a cluster of stars, a group of stars, okay? And you study which ones you can study, and there are a lot of them. And you catalog them, you put them in some sort of a nice table. And that's the purpose of the HR diagram. Again, these are stars, you're looking at a patch of the sky. So you're not looking at the entire sky, by the way. And you put them on a diagram, typically an HR diagram, which is the Hertzsprung-Russell diagram. There are a lot of diagrams, by the way. You will find that the temperature is decreasing in the y-axis, meaning hotter temperatures are first, and then as you move along, it's going to be cooler and cooler stars. Temperature. Number two is the luminosity in here. It ranges over a huge scale. So what you do to tame it, you use what is known as a logarithmic scale. The transition between one level and level is actually 10 times bigger than what appears to be. So if you find one gap in here and another gap that appears twice, the difference between the two is actually 10 times in this case, because we just doubled it. Okay. Doubled it means it's 100 times. I'm sorry. One step is 10 times, two steps is 100, three steps is 1,000, and so on and so forth. If you go in the opposite direction, you're dividing by this number. So that's an important thing, because the scale is really unmanageable if you put it on a linear scale. So you have to use a scale. So this is in a nutshell what it is. So what do we find in here? Most of the stars, they fit on this diagonal. And the diagonal is going from extremely cool stars, less bright stars, smaller in size stars, less mass stars. So these are temperature less than 3,000 Kelvin, to temperature stars that are over 30,000 Kelvin, extremely hot, extremely big, extremely massive stars. They fit on this diagonal, which is called the main sequence stars. That's most of the stars. Extremely small stars that are the size of the Earth physically, and in terms of size. In terms of mass, they're much, 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 much larger than that. Okay. Those stars are called white dwarfs. And these stars are the remnants of this main sequence stars that happen to be of a certain size that end up being in here on this side of the spectrum, on this side of the diagram, I'm sorry. And there are a few stars that are cold on their surface, but huge. They're red, and they're giants. They're called red giants. They're even bigger than that, called red supergiants. There are actually blue giants also in the spectrum, and they are yellow giants in here. So these are the main classifications in this diagram. So remember the following, that the temperature is cooler as you move away on the x-axis. The temperature is hotter and you're closer to the origin of the x-axis, okay? That's one thing. Furthermore, the scale on the y-axis is not linear, meaning between one and this point in here that appears to be only one gap, there is a difference of 10 times more luminous than had it been one. One with respect to what? With respect to the sun. So the sun sits exactly at 1. This is the sun. And the sun, its surface temperature is about 5,800 Kelvin. I'm sorry, it's about 5,800 Kelvin. Again, I made a mistake. It's on this side of the 5,000. So that's roughly where the sun is. Okay. So anything brighter than the sun is sitting above the sun. Some of them are about 1 million times brighter than the sun. More luminous than the sun, I should say. Some of them are extremely less bright. They're about 10,000th that of the sun. Okay. So that's in a nutshell what we're talking about here in terms of this diagram. So again, this scale from here to here is 10 times. From here to here, this appears only twice, 2 jumps. It's about actually 100 times. From here to here, this appears 3 jumps. That is actually 1,000 times more brighter, and the opposite is true in here. So this is what is known as a logarithmic scale. Okay, this is a logarithmic scale. Now note these letters O, B, A, F, G, K, M. This is the spectral classification that was put by Ms. Cannon in before we know about the temperatures and all of these things based on their spectral lines. This is part of the lab that was discussed yesterday for those sitting in Astronomy 125. And these divisions, we're going to come back to them. They have their own subdivisions themselves. For example, the sun happened to be a G star, but it's actually a G2 star. It's kind of a hot really compared to the rest of the G stars. 5,800 Kelvin, because the G classification starts from 6,000 all the way down to 5,000. And the sun is 5,800, which is just on the upper end of that range. So it's a G2. G, and this scale also is, as it increases, it's less and less temperature. So that means a G3 is less hot than a G2. And a G2 is less hot than a G0 and so on and so forth. So that's the classifications of these stars. Again, this is the HR diagram, and it's a very important, it has a lot of information in it. So that's one thing. The other piece of information is in terms of the groupings. There are families of stars. First of all, the unknown stars. Proxima Centauri, which is the closest star, is here. Some of you sitting in Astronomy 125 recognize the star, Bernard star. This was one of the stars that we studied extensively yesterday in the lab. And for those sitting in Astronomy 125 section 2, that's also going to be explored with them tomorrow. We did the Procyon also. We did also Ceres. When we did Ceres, we combined the two series A and B, which are part of actually part of a binary system, and I mentioned them in the beginning today. They are part of a binary. So when we looked at them, we saw their classifications. We did also Arcturus, and we did also Betelgeuse, and there were other stars that are not mentioned in here. Procyon also is part of a binary similar to a Ceres. And also when we did that, those turn out to be of a different classification, not the group 5 stars, but they turn out to be group 3 stars. So again, not group, but spectral group, that is, okay? Main sequence versus non-main sequence stars. So this is basically how the grouping again is, and all of this is the spectral classes versus the spectral type, I should say. Okay. Now, this also diagram has a representation of the sizes too. Okay. Again, the sun is the standard. The sun is the candlestick with which everything is measured. Otherwise, you'll have to remember that the sun's radius is 696,000 kilometers, and Alpha Centauri A, which is slightly bigger than the sun, a little bit more massive than the sun, versus Alpha Centauri B, which is slightly less massive than the sun, slightly less size than the sun. So that's it, just below this line. So, but all three stars, they are roughly the same size. Okay, they are actually a part of the same group. They are all G stars. Granted that Alpha Centauri A is actually of a higher temperature than that of the sun, and Alpha Centauri B is of a less temperature than the sun. All of this correlates also to the age of the stars. Vega, which is another important star, the main sequence star, actually happened to be a lot hotter than the sun. Series A and Series B are part of a binary, and these are what is Aldebaran? Aldebaran is actually here, the eye of the Taurus. Polaris, which is the northern star, is in here. Then Rigel. Rigel is part of the Orion constellation, and Betelgeuse is also part of the Orion constellation. And all of this are some of the stars and how they range also in terms of their sizes too. Obviously, 1,000 times bigger than the sun is a huge size for Betelgeuse compared to the sun. Versus, for example, Proxima Centauri, I'm sorry. Proxima Centauri, which is about a 10th, which is about the size of Jupiter, actually, in terms of physical size. But it's much more massive than Jupiter, of course. It's a star. Okay, in terms of luminosity, it really also depends on the mass of the stars. This is also represented on the y-axis too in this case, and it's actually, as I was saying before, it's really a logarithmic scale. What you need to know is that the less massive stars, they burn slowly and they live a long life compared to the hotter stars that have burned very quickly and they die very quickly. We will see later on that this is actually how regular, at least mid-sized stars end up to being white dwarfs. We will see that this big star, they will end up in one of two other scenarios, either as black holes or neutron stars. So this is in a nutshell what the diagram is telling you. It's giving you all kinds of information of how they're, the more massive, of course, they're brighter, the less massive, they're dimmer. And that's really what all of this information is carried in this diagram. It's very important classifications. Again, this is the luminosity as a function of mass. It's important to remember this relationship, that the luminosity of a mass is equal to the mass under the square root, but raised to the power 7. So this is a normal square root that you do. Granted, the luminosity in here is expressed in terms of the sun, the sun's luminosity, and the mass also is expressed in terms of the mass of the sun. This is an important point of information because down the road in the next units will determine the life of a star. And it's going to be proportional to also the mass of the star, but it's also going to be inversely proportional to its luminosity. The faster it's going to burn, the less life it's going to live, basically. But the bigger star, for the same luminosity, should live a little longer times a constant. And the constant is actually the age of the sun. So, okay. So this is basically some of the quantitative measurements that you have for the stars. And again, the luminosity, it depends also on the size too, not just the surface temperature. And these are far more luminous, although they have dimmer temperatures in general than that of the sun. Okay. So again, the classes in this case, you have class 5, which are main sequence stars. So in the lab yesterday, we were supposed to only calculate it for the main sequence stars, but you also have the subgiants, which are Procyon. Procyon turned out to be not a class 5, but class 4. And then you have the ordinary giants like Arcturus in this case, and the Bootes. And then it's called Boites, I think that's how they pronounce it. And then you have Polaris, which is a bright giant in the classification 2, and 1A and 1B, those are the supergiants or the bright supergiants, Antares and in the Scorpion, and also Betelgeuse and Rigel in Orion. So these are some of the classifications. Again, for those sitting in the lab, this is basically what the lab dealt with. In addition to, based on when you determine that the star is a main sequence star, you're supposed to find how far it is. If you guys, again, this discussion is not relevant to everybody, but at least those sitting in the lab, from here you can find the star, basically how far it is, the distance, using this formula, where you're supposed to find V minus M, the brightness of the star minus that of the standard plus 5, which is part of the formula, divided by 5, and the answer is going to be in parsec, not in light years. So again, that works only for the main sequence stars. We still have a lot of materials to come, so I'm going to try to record most of the stuff that is relevant for the next few minutes because we're left behind, honestly. I'm going to do that. This is not in lieu of reading. You still are required to do your reading. You're still required to do your assignments to make sure that the content actually is gained. And I will follow up with messages. Please reach out to me if you find something is not clear or something you need help with. Please reach out to me as soon as possible. Don't leave it to the end, then you're going to be running out of time to make up for assignments. Thank you.